Picking up right where we left off, discussing the vibration of polyatomic molecules. So I know that you've talked about this in OCHEM, ad nauseum. But of course, in this class, right, we're going to add a little PChem twist to topics that you've already previously discussed. And so my two favorite molecules, H2O and CO2, I'm going to use these as good examples to discuss the vibration of polyatomic molecules. So first, I want to introduce this concept of normal modes, and I realize I should have had a definition up here, so I'll read you a definition. So a normal mode is an independent, synchronous motion of atoms or a group of atoms that may be excited without leading to the excitation of another normal mode. So in other words, these normal modes, these modes of vibration, as we said, are independent, synchronous motion of atoms or groups of atoms, and each normal mode, the word independent, right, it's independent from the other normal modes, okay? So these vibrations are all separate energy transitions, okay? And so there's a couple of equations for the simple polyatomic molecules. 3 and minus 5 normal modes for all linear molecules, and 3 and minus 6 normal modes for all nonlinear molecules, where n is the number of atoms. Okay, so for example, with water, we know water has 3 atoms, so 3 times 3 minus 6 is 3. Okay, so water has 3 normal modes of vibration, and here they are, right, that we affectionately know as the symmetric stretch, that I'll write sim. Okay, and so typically that's given as nu sim for the symmetric. We know there's, and let's demonstrate that, right? So if my oxygen, or my torso is oxygen, and my arms are hydrogens, right? The oxygen kind of moves down just a little bit while the hydrogens come in, okay? And even though this is a symmetric stretch, it does end up creating a dipole moment because we know that water is asymmetrical. So this is observed in IR spectroscopy. And for an isolated gas phase water molecule, a singular molecule in the gas phase, this would occur at 3652 wave number. And so this number right here, that would be the Q branch, okay? In a single gas, right? An isolated gas molecule. Of course, when this vibrates, it'll stimulate the rotations in the gas phase, but this would be the line associated with the Q branch, okay? So, and then of course there is the asymmetric stretch, typically written as VA sim, or sometimes just nu asim. Sometimes it's just written as nu AS. So some kind of qualifier to let you know that's the asymmetric stretch. And my oxygen kind of moves, oops, I'm looking at my reflection. I should just focus on what I'm doing. So an oxygen moves in like this with this hydrogen elongated, and then it alternates, okay? So I like to think of these as like the interpretive chemistry dance moves, right? So this is a nice symmetrical stretch, okay? And it occurs at very similar energy as the symmetrical stretch, 3756 wave number. And then finally, the third and final normal mode of water is the bend, right? Where now these things will bend in and out of a plane, okay? And consequently, that's a much lower energy stretch. And so what we want to think of, these actual energies or frequencies, they are related to the frequency in which a bond is oscillating, and that is the frequency of light required to stimulate that vibration to go up to an upper level, okay? Where it will oscillate then at an even higher frequency in that upper level. So that 3652 wave number, for example, right, is the energy required to stimulate that vibration to vibrate at a higher frequency relative to its ground state. Okay. So if we look at carbon dioxide, we also know it's got 3 atoms. It's 3 n minus 5 because it's a linear molecule. And so 3 times 3 minus 5 equals 4. So 4 normal modes for carbon dioxide. So we know that there is the asymmetric stretch, right, which is shown right here. Okay. So V asym. Right, and similarly to the water, this is when one bond compresses and the other bond is elongated, and then it recoils, okay? So we've got this nice, lovely asymmetric stretch. Of course, that also means we have the symmetric stretch, right, where it just does this, okay? And as it turns out, oops, I think I labeled these incorrectly. I labeled these incorrectly because that symmetric stretch for CO2, notice it doesn't have an energy associated with it. That's because it's forbidden. So it does not result in a dipole moment. So it's not observed in FTIR. Okay? But as it turns out, this stretch is observed in Raman spectroscopy, which we'll be discussing next. Okay? So here, at 2349 wave number is our asymmetric. Okay. Yeah. And then finally we have the bending mode. Okay. So if we count up these number of modes of motion, we've got 1, 2, 3, 4. Okay. So this asymmetric would occur. I'm sorry, I was talking to my son back there. It would occur at 1388 if it were observed, but it is not observed, so we don't see that. Okay, apologies for that confusion. But at 2349, that's our big prominent CO2 peak that we see not only in FTIR spectra, but what's also principally responsible for the greenhouse effect. Okay. So that's the strongest line for CO2. And then there's 2 bending motions, right, where I can either do this or this, but because CO2 is linear, those are both degenerate. So let's label that new bend, and here, of course, I forgot to say new bend. Okay, and this normal modes, right, that just predicts how many normal modes we have. It doesn't necessarily tell us how many peaks there will be on the IR spectra, because we have to remember our selection rule that there's got to be a dipole moment. All right. So I want to keep picking on this example of water. Water is just a fascinating molecule. There's still loads and loads of active current research going on, trying to just understand the nature of water from a molecular level. And of course, how water influences biological systems, environmental systems, engineering systems, and so forth. So water, always an interesting example. So here we can see those normal modes. And these energies, like I said, these would be for isolated gas phase molecules. Okay? So the first thing I want to point out is the vapor. And so we can see here, these are all of the rotational lines. Because since it's a vapor, a gas, we're going to see that those vibrations will stimulate the excitation of a rotation. Okay? So water as a gas is going to exhibit these nice rotational lines, and also its stretching frequencies. So here we're only seeing the stretching frequencies out at 36 and 37. Okay, the bend, right, we're not even seeing on this scale. But those, for water vapor, those will occur at higher energies. So those bonds have to vibrate at a higher frequency. And they're generally, as a vapor, not really being influenced by anything else, assuming we're in the ideal gas regime, right, where other neighboring water molecules aren't influencing each other. So what you're seeing right here is a confluence of J terms J plus minus 1, and all we're seeing is from nu 1 to 0. Okay, but because we have two modes here, there's the symmetric and the asymmetric. There are two sets of P, Q, and R branch going on these vapor lines. And so that's why it looks chaotic. So doing a P, Q, R branch analysis on this would be quite difficult because of how complicated that system is. Okay. So now if we look at liquid water, okay, it looks like we've just got one big continuous peak here, but in fact there are two underlying peaks. Okay, so I'll point to this liquid and we'll say it's convoluted. So in other words, the symmetric and asymmetric stretch are occurring at very similar energies, and they're right on top of each other, right? We can see for an isolated water molecule, those are only about 100 wave number difference, which will be similar as a liquid. However, they're now shifted to lower energies, and that's because the presence of other neighboring molecules can assist in those vibrations, right? We've got other molecules nearby that can help push and pull those vibrations. So an FTIR is a fantastic technique for working out intermolecular force details. Just by the simple observation of seeing how these phases shift to smaller energies, right? Remember, smaller wave number, smaller energy. So high energy, low wavelength, low energy, high wavelength. Okay? So, but what's really going on with this liquid water, we have to do what's called spectral deconvolution. So we need to separate these two peaks. And the way we do that is by fitting this with a set of Gaussian functions. And this is what you're doing in your Spec 1 assignment. Okay? And so really we recognize that there is, a peak associated with the asymmetric, and there's a peak associated with the symmetric. Okay? And both of those are occurring at very similar energies. Both peaks are really broad, and the reason why they're broad is because water is quite chaotic as a liquid, right? The presence of these other neighboring molecules can influence the energies to not necessarily occur exactly at a quantized frequency every single time, right? If we had single isolated molecules, we would certainly see, right, single lines. But therein lies the rub, right? By definition, we can't have a single isolated liquid molecule. Okay. And so now when we look at ice, you can see ice continues to shift to lower energies. It's much more rigid. Okay, so those bonds are a little bit stiffer, but also get some assist from neighboring molecules, right? And you also notice that the symmetric and asymmetric stretches are in different proportions, right? So if I were to try to do a deconvolution on this, perhaps I can see that the asymmetric stretch is giving rise to this shoulder. So we give all kinds of creative descriptions to features in spectroscopy. So typically when you see a feature like that, we call that a shoulder because it literally just looks like a shoulder. So perhaps the asymmetric stretch looks something like this at lower intensity, and the symmetric stretch, right, is occurring, way up something like this. Okay. And of course, we know that what we really observe in spectroscopy, right, is the total. So when both of those get added together, right, we see the constructive interference of both of those peaks. So deconvolution is the process of fitting our spectral data to multiple, typically a Gaussian peak, but in some techniques, a Lorentzian is acceptable. A Lorentzian is best described for the Doppler effect. And all of this is described in your Spec 1 assignment. There's lots of nice background info to get you going on this. Okay. But even if we weren't looking at just simple arrangements of molecules like vapor, liquid, ice, suppose we were looking at really complicated arrangements of molecules, perhaps some intermediate in a chemical reaction, or some molecule adsorbed to the surface of something, right? So we can also use this deconvolution process to work out those types of details when we have non-trivial arrangements of molecules, okay? So moving on. So let's get into Raman spectroscopy. So I always like to really point out that this is not Raman or Ramin. For 10 years, I've been listening to students mispronounce this. So this technique is named after Chandrasekhara Raman, an Indian scientist. He won the Nobel Prize, so it's C.V. Raman. He was the first Asian to win the Nobel Prize in 1930. Pretty cool. And so he won this Nobel Prize for his descriptions of light scattering, particularly this notion of how we can use scattering as a form of spectroscopy. So let's describe this, because this is a very complicated effect. Okay? So it starts by bathing a molecule with incident EM radiation, right? And typically visible light is used to best drive this technique. And because light is an oscillating electromagnet, right? We know that there's little oscillating dipoles. When there's a really intense field of light bombarding a molecule, it can actually distort the electronic environment. Okay? So this shaded area that you're seeing are the MOs, the molecular orbitals, getting distorted from their resting, room temperature ground state configuration. Okay? So this light distorts the electromagnetic field. And as a result, it actually then scatters off of that electromagnetic field. And I've drawn this to look like a grating because, in fact, what happens in this technique, it's really like a molecular grating. Okay? So it doesn't quite work the same way as the grating equation where we consider the different indices of refraction. But all of the same, it's very similar to that in that it is a scattering technique. This is not an absorption technique. It's scattering. Okay? And so these are the rules for rotations. So we can have rotational Raman or we can have vibrational Raman. So these are the quantum numbers for rotational. And I'll describe how that's different for vibrational. Okay? So for the J equals 0, so if there's no effect on the rotational state, we just call that Rayleigh scattering. And there's no effect. So if the incident radiation is coming in at, let's say, 532 nanometers, the Rayleigh scattered light will also come out at 532 nanometers. So, and the reason why I pick 532 nanometers is because that is a green laser light, which is typically used for the Raman effect. Okay? So that 532 nanometer green laser works universally quite well for most molecules. So the Rayleigh scattered light will also be 532 nanometers. Okay? And in fact, the Rayleigh light scattering effect is the description of why the sky is blue, right? There's very small molecules out there. And so the atmosphere is made up of very small molecules, particularly nitrogen. Nitrogen is the right size to scatter blue light quite effectively. Okay, so here we have white light coming in from the sun, and all of this light is scattered off, right? Rayleigh scattering, but the blue in particular is scattered the most effectively. Okay, so that's a simple description of why our sky is blue, and in fact, any other celestial object that has an atmosphere containing nitrogen will also be blue, right? Which is pretty cool. So now, when the rotational levels are affected, the J, when it increases the rotational state, we call that the Stokes shift, and when it decreases the rotational state, we call that the anti-Stokes shift. Okay, so if we look at this on an energy level diagram, this becomes a little bit easier to understand. And so we draw this energy level diagram by noting that the light is being scattered off of a virtual state. So that virtual state is really like the polarized electronic environment, right? It's those distorted MOs, okay, that create what we call this virtual state. And so now the Rayleigh line, right, is just simply if we're using one color, right? So this is assuming one color, right? Then there's no change in that effect, okay? And so here you can see a spectrum of intensity versus Raman shift. And if we were using 532 nanometers, right, as our incident radiation, then for the Rayleigh scattered line, lambda 1, the scattered wavelength, is going to come out right at 532. And this will be the most principally observed light. And what I also want to point out, when I draw a little, I'm going to draw our little detector here, okay? And our detector is detecting visible radiation. It is looking for that 532 or thereabouts wavelength. All right? So that is as you can see, that 532 peak, it blows out this scale. So typically you would use a filter to block out the 532 wavelength. So block out 532. Okay? So now, what is the deal with this Stokes shift? All right. Well, if we scatter that incident radiation off the electronic environment, and when it relaxes, if it relaxes down to a higher rotational level, or it could be a higher vibrational level, right? In terms of J's, it's got to be plus minus 2, but in terms of vibration for the Raman effect, right, it's just plus minus 1, okay? So if this were vibrational Raman, I would replace these J's with nus, and this red line would go down to the nu equals 1 state. So in other words, it's leaving the molecule in an excited state. Okay? And so what that means is that Stokes light that comes off, right, the Stokes shift, is going to be less than 532. Right? Just based on the size of this, right? So if I ID this as lambda 0 and this is lambda 1, you can see now to look for the Stokes shift, I would set my detector to look for wavelengths less than 532 nanometers, right? Because of that diagram. However, I'm also at the same time going to be getting anti-Stokes shifts, where in other words, because now I've left the molecule in an excited state, or because of just simply its rotational population of states, right? If this is the rotational lines, then right, these molecules exist in these higher lying levels. And in the case of vibration, well, the Stokes shift puts it in an upper lying vibrational level. Okay, so anti-Stokes starts at a higher level, and the result is that a bigger energy comes out. Okay, so you can see in the anti-Stokes, right, those all look like negative numbers, whereas in the Stokes they look like positive numbers. And so here's how we calculate those Raman shifts. And so I've got it here coded up, and I think I actually need to put 530 in there. So let's suppose that, just kind of playing around with this. So let's suppose we shine some 532 nanometer light on our molecules, okay? And then we detect that Stokes shift. So we detect something at 530 nanometers, let's suppose. So what is it that could have given us that 530? And I'm just pulling those numbers off the top of my head, right? I'm just saying, suppose 532 comes in and we detect a 530 nanometer photon going out. Well, if I calculate that Stokes shift, which would go 1 over 532 minus 1 over 530, and so let's take away that factor 10 to the 7, because that would be 1 over nanometers. So I get this crazy number, negative 7 times 10 to the minus 6 inverse nanometers, right? So let's say that's negative 7.09 times 10 to the minus 6, 1 over nanometers is the way that's going to work, right? Well, we know there's 1 times 10 to the 7 nanometers in 1 centimeter, right? So if I multiply this by a factor of 10 to the 7, that's going to put that in units of wave numbers, okay? So that means that if I detected that 2 nanometer difference, then that means I would have had to have, that's wave number. That means that there would have been some vibrational or rotational, but based on these numbers, 70 wave number, that's a vibration. So vibrational normal mode. That's exactly what would have resulted in detecting that 2 nanometer shifted photon, that there was some vibrational mode at 71-ish wave number, okay? Which is pretty cool. And so, of course, in the Stokes shift, right, because this graph is actually showing us vibrations, just, again, based on the Raman shifts, okay? Then I would see the corresponding positive peak, which is also kind of cool, right? And so typical, Raman shifts, they're going to correspond to the vibration. So we're going to see Raman shifts that are like, a couple thousand wave numbers, okay? So here's a great example. So here is the IR spectrum of CO2, right, where we're seeing new asymmetrical and we're seeing new bend. Well, as it turns out, neither of those modes are Raman active because they don't disturb the electronic environment enough. However, the new symmetric stretch is Raman active, right? And recall we said that, that one is at, so let's back up here and let's put some labels on these, right? So the 667 and 2349, so that's 667, and this one's 2349. But that symmetric stretch would occur at, it was 13 something. 1388. Okay, so that one is Raman active. So this is really cool about the Raman effect or Raman spectroscopy, is that we can observe modes that might not be observable in FTIR. Here's another great example of the Raman shift for benzene versus the FTIR. And you can see that there are some peaks that match up and some peaks that don't. So some of these peaks are Raman active, some of them are IR active. Okay? So these serve as great diagnostics when you can do both Raman and IR. Sorry, I'm just checking my time here. Then you can get a really nice positive ID on a molecule, especially if it's a molecule that hasn't ever been synthesized before. If it's a brand new molecule, you might not be aware of all of the active FTIR modes or Raman modes, right? Or, as I alluded to earlier, if it's a complex arrangement of molecules, perhaps it's some novel phase, right? Or some novel arrangement. Doing both techniques would give you an ultimate characterization of the molecule. Okay, so let's move forward. I know I've been talking a while, but I want to just now spend just some brief time talking about the different FTIR spectroscopy types. Will just be very brief. Okay. So the first one, transmission, I would wager that none of you are aware of this technique because this is old school. I'll say school. But this is how I learned how to do FTIR as an undergrad. Okay, so salt optics work best for IR because they are IR transparent. So when we look at these nice, fine, pristine optics, those are actually sodium chloride solid. And I love this figure here. You can see if we start with just some crystalline sodium chloride, and we add a lot of pressure and a lot of money because it takes time to do these and quality control, then you end up with this beautiful transparent disc. Now, sodium chloride is okay. KBr is best. And that's due to the hygroscopicity. So sodium chloride takes on water. That's what hygroscopicity means. It'll take on atmospheric water. And once these things take on water or any other material that it is soluble in, your optic is ruined. So you can see this person cleaning this optic. Typically, they use a long chain alcohol. Isopropanol is usually okay, but these salts will not be nearly as soluble in the longer chain alcohols as they will be in water. If you were putting water on your salt optic like that, you'd be totally screwed. But KBr is far less hygroscopic than NaCl, and it gives you nice, lovely looking optics. And I use KBr exclusively in my lab when I can. I should say, let's do it like this. Sorry, I'm going to change my little qualitative. We'll say this is okay, this is good, and the piece de la resistance, zinc selenide. That's the jam. Zinc selenide makes lovely salt optics, and it is chemically resistant to everything. So you could expose this stuff to ozone. You could expose it to fluorine radicals. You could expose it to UV light, and it will not degrade. Okay? It is also extremely expensive, even more expensive than our salt optics here. And it's very brittle and easy to break. And I'll share a story with you. In grad school when I was doing some transmission FTIR with zinc selenide optics. I broke 3 $500 zinc selenide optics in one day. So anytime that you break a beaker, anytime that you've damaged something, I guarantee you haven't broken $1,500 worth of salt optics in one single day. Okay, so here's what happens with these salt optics and why we use different techniques now. So pressing these things, or even when they become damaged from atmospheric water, or even sodium chloride is suspect to being oxidized. When it gets oxidized, it'll release chlorine. So you can see how an IR spectra, a transmission IR spectra, right, will become quite crappy as your salt plate degrades. Okay, so that's why zinc selenide is the best for transmission. But you guys didn't do any of this because we don't have a transmission accessory. And what I want to point out, right, all FTIRs are the same. They're all the same garden variety instrument. that uses the Michelson interferometer. What makes various types of IR special are the accessory. Okay, so this is a transmission accessory. It's just a little device that can hold two sandwiched optics. So that's the lingo, that's the terms we would use. So this would be your analyte, right? A little drop of your analyte right there. And you would sandwich it between two optics, much like you were preparing a cover slip for microscopy, right? And you put it in this little accessory that holds those two plates together, and you pass a beam right through it. And so, as you also might imagine, this is not quantitative at all, because you have no idea what the path length is. Okay? So this is the type that we have at HSU Chemistry. Okay? That FTIR that you used up in the OChem lab is actually called an attenuated total reflectance. It's called an ATR. It's still a garden variety FTIR, but it takes advantage of total internal reflection. Okay? And recall, we described this earlier. Total internal reflection occurs when you're at, right, this magic angle that allows a beam to pass right through. And typically it's passing through your optic. So this is your, ATR crystal, but that's your optic. And that could be a salt optic. That could totally be a piece of sodium chloride, potassium bromide, or zinc selenide is the best. Okay? So this is called a multi-bounce ATR crystal. This is the type that we have. We have a single bounce. And now if you can picture that IR up in the OChem lab, right? You spike your sample right down in that little cup, and you put the press over it, okay? And the IR beam actually comes up from underneath through this crystal. The one that we have at HSU is actually a diamond, believe it or not. So that's even better than zinc selenide because it's not going to get damaged. Crazy expensive, okay? As you might imagine, it's a diamond. And also, you don't expect it, but diamonds are IR transparent because carbon is not going to interact with an IR beam, right? A pure carbon lattice, there's no dipole moments, there's no asymmetrical stretching. So an IR beam will pass right through it, okay? Which is pretty cool. And so you just get a single bounce off of this. So, and it does just fine for your detection. And again, not quantitative, okay? Very difficult to be quantitative with this technique. And the main difficulty of being quantitative with IR is just because the path length. You have no clue what this path length is. Same with the ATR. And now the multi-bounce is for really low concentrations, or even for molecular level detection. So for example, there's lots of cool studies out there where people have taken these ATR crystals, oops, I'm going to draw like a parallelogram, and they actually bind molecules to the surface of these things. I'm just going to show like generic molecules being bound here. So people will actually do some surface chemistry on their ATR crystal. They'll actually chemically bond some molecules to that ATR crystal. So one singular molecular layer. And if you get enough bounces out of your ATR crystal, you can actually detect that single molecular layer of molecules with this ATR technique. So it might not be quantitative, but it's extremely sensitive. Okay? And so the final technique that I'll describe, and I know, like I said, I've been talking for a while, so I hope this is, this is interesting for you. So this is what I take advantage of in my own lab, which is called drifts. And I love this acronym. So as I like to tell people, if your technique has a cool acronym, that means you're doing something hip and modern. So drifts stands for diffuse reflectance, infrared Fourier transform spectroscopy. And once again, this is just garden variety, regular old FTIR, but it's the accessory that makes it special. So this is our drifts accessory. Okay? And so it's just this complicated little device that gets placed in the sample compartment of an FTIR spectrometer. And so again, recalling our photophysics, diffuse reflectance, right, is when we have non-specular reflectance, right? So we have a rough surface, and as each beam of light comes in, it scatters off of the surface normal. Okay, and you can see that that's being highlighted here. So drifts is used for powder solids, and powder solids only, because if you have a smooth surface, if you have a smooth solid that you put in there, you're going to get predominantly specular reflectance, okay? Which could also be a technique, but that defeats the point of doing diffuse reflectance, right? So diffuse reflectance is for powder solids, okay? And so you can see a powder solid like this, right, will have lots of spaces in between. And so the light gets scattered around in all different directions, including even into the solid. And so because of this, what happens is you have a very small, what's called sample depth. In other words, the IR beams that scatter back off the surface and eventually make it to the detector. So again, you can see it's a very convoluted set of optics. And it is no easy task aligning these optics to get the light to come in, bounce, scatter off the surface, and make it to your detector. This is not a fun job. Luckily, my students did it for me. So that's a good rite of passage to do spectroscopy, to align the optics of something like this. Okay. So, and you can see actually this elliptical mirror, you can see it right here. There's the elliptical mirror, okay, which is pretty cool. And so that elliptical mirror will close over this sample holder. So this little device you're seeing right here is our solid sample holder, okay? And so our sample depth is typically only about 1 micrometer. And so what that means is the IR beam that's scattering off the surface that eventually makes it to the detector is only coming off the first micron or so of the sample. So that makes this a surface sensitive technique. Similarly, ATR, the ATR technique I just described, that can also be used for surface science as well, as I described. If you do some very careful chemistry on your actual ATR crystal, that can be done for even smaller than 1 micron, right? You can detect molecular layers with the ATR technique, okay? And so now this technique is most useful if you want to, for one, investigate powder solids, but two, where this technique really has a lot of use is in doing action spectroscopy, okay? So I just want to spend just 1 or 2 minutes briefly plugging my own research, okay? So here you can see we've got, you can see what zinc selenide optics look like. So here they are. They're this lovely yellow color. So it doesn't matter that it's yellow because all we're worried about is transmitting an IR beam, not a visible beam. Okay? So this is where this technique is really powerful. We load our powder solid in this sample chamber. And in this drifts sample cup, we have this little lid that goes on top that can completely isolate our system. So it can isolate it from the atmosphere. So you notice here that I could, if I want to, I could pull vacuum on this thing. So this goes to cold trap and to a pump. So we could actually pump down our sample chamber to a vacuum, which is pretty cool. And what we can also do is using a complicated set of gas flow lines. So that's what all this stuff does, which is all housed in this white instrument rack right here. So all of this stuff is just a way that we can deliver a mixture of gases that we're interested in with precise distributions. So if I want to make an 80-20 nitrogen oxygen environment, I can. If I want to make a 5 part per million carbon dioxide environment in air, I can, right? That's what we do with this manifold. And now we flow the gases over the surface. And so the gases flow over the surface and then make it out through the exhaust. And because our IR beam is being scattered off the surface, and because our path length is really small, we don't really see what's in the gas phase. Rather, we see what's occurring at the solid interface, right? We're seeing heterogeneous chemistry as the gas passes over the solid in real time. And this is it's identical to the technique I showed you with that sulfate oxidation reaction. Okay, so that's where I got my inspiration. And here's kind of what some data looks like, right? We see dynamic spectra where negative peaks indicate we lost some functional groups, and positive peaks indicate we gained functional groups. And you can see here, this is just sample spectra from some chemistry that I'm not going to describe, but you can see it's very dynamic, right? You can see at 6 minutes of ozone exposure to some solid interface, some hydroxide stretches grew in. At 22 minutes, hydroxide stretches grew in even more. But then interestingly, at 36 minutes, they all went away, and at 51 and 66 minutes, we lost all of those hydroxide stretches. You can see we also lost some carbon-hydrogen stretches as well. You can see here, that's the gain of CO2. So we can study lots of complicated chemistry in real time using this technique. And again, I'll remind you, the way we put this together, our sample is our background, right? So we just only load in a sample. We don't even do a background. We just load in a sample. We flow like just an inert environment over the surface, and that's the background spectrum. And then we change that inert environment to some, right, chemically oxidizing environment, for example, right, something that's going to actually induce a reaction. And then we record single beam spectra in time and ratio those to the original background spectra. And so that's how we do kinetics in my lab using the drifts technique. Okay? So I've been talking an awful lot, and apologies for that. That's the last lecture for this week. I hope this was all interesting to get a little bit of a different perspective on this FTIR technique that I know that you've talked so much about. Okay. All right, folks, I'll see you later.